Since 1986, DNA profiling has been a powerful identification tool for linking criminals to the scene and to their victim. However, a jarring limitation of the conventional SDR profile is that without a reference profile from a DNA database or a person of interest, it provides no informative data for the criminal investigation. This restriction has recently been overcome. The rise of next-generation sequencing technology has made it possible to predict the phenotype and ancestry behind the donor of the genotype and create a molecular photo fit. From a forensic point of view, these predictions provide numerous benefits. It is now an option to substitute a photo fit for an eyewitness testimony should it be unreliable. Investigators can access fresher insights for cold cases, and they can assist with more accurate identifications of missing persons and mass disaster victims. So, how is this all possible? In an effort to analyze 6 unknown DNA profiles to create a molecular photo fit, DNA was extracted and purified using the Automate Express machine. The DNA was quantitated with the 7500 real-time PCR instrument. The Precision ID Ancestry Panel by Thermo Fisher Scientific and the Ion AmpliSeq DNA Phenotyping High-Riskplex Community Panel were utilized to create a library of informative SNPs. The panels, primers, and library were prepared using the Ion Chef system, with adapters, barcodes, and binding sites being ligated to each fragment and undergoing PCR. This was loaded onto an Ion Chef chip. From here, multi-parallel sequencing using the Ion semiconductor was performed as shown here. The sequence was extrapolated using the Ion Torrent platform and digitally viewed using Torrent Suite software. The genotypes were then analyzed for phenotype using the High-Riskplex web tool and for ancestry using the Snipper app suite in conjunction with the Precision ID Ancestry reference genotypes. As an overview, a principal component analysis is provided, which works by mathematically converting the data obtained from reference populations into uncorrelated variables that effectively represent genetic divergence and relatedness between different populations of the world. Individuals 1 and 2 are predicted to be South Asian, individuals 3 and 5 to be European, and individual 6 to be East Asian. Strangely, individual 4 does not fall into any regions of ancestry according to the PCA plot. Results such as these are usually attributed to genetic admixture, where DNA from a distantly related population is present in the individuals of another population. Admixture can result from events such as natural selection and migration, which create unique phenotypes. As undetected mixed genotypes and complex admixtures can displace individuals, it is necessary to use the plot to assess the reliability of the results. Individual 1 is predicted to be European, with an admixture of 98.6 European and 1.04 South Asian. They are 94.92 times more likely to be European than South Asian, and more than 1 billion times more likely to be European than East Asian. This is contradicted by the PCA plot, which suggests they are South Asian and indicates increased admixture. They are predicted to have light brown or dark brown hair, with an 81% probability they have brown eyes. Individual 2 is predicted to be South Asian with no admixture, aligning with the PCA plot. They are more than 1 billion times more likely to be South Asian than both East Asian and European. They are predicted to have light brown or dark brown hair, and with 98% probability they have brown eyes. Individual 3 is predicted to be European with no admixture, agreeing with the PCA plot. They are more than 1 billion times more likely to be European than both South Asian and Oceanian. There is a 97% probability that they have blue eyes, however hair color cannot be predicted. This is due to an unsequenced SNP that evidently plays a large role in the prediction of hair color. Individual 4 is predicted to be South Asian with no admixture. They are more than 1 billion times more likely to be South Asian than both African and European. Although these results seem convincing, the absence of the individual in a population cluster on the PCA plot suggests there is admixture outside of the reference populations used. They are predicted to have dark or black-brown hair, with a 99% probability they have brown eyes. Individual 5 is predicted to be European with no admixture, aligning with the PCA plot. They are more than 1 billion times more likely to be European than both South Asian and Oceanian. They are predicted to have light brown or dark brown hair, with an 81% probability they have brown eyes. Individual 6 is predicted to be East Asian with no admixture, aligning with the PCA plot. they are more than 1 billion times more likely to be East Asian than American or South Asian. They are predicted to have black or dark brown hair with a 79% probability they have brown eyes. So, just how reliable are these types of results in the forensic world? These results would be beneficial in narrowing down a list of pre-existing suspects. However, in cases where DNA is the only evidence available, it would be improbable to identify a suspect based off eye color, hair color, and ancestry alone. Although the results are informative on these traits, it fails to take into account modifications to the natural appearance, such as hair dye and environmental factors affecting phenotype, such as sun exposure. Also, the ancestry data becomes vague and more difficult to interpret when considering biracial or mixed individuals who stray from this typical phenotype. In conclusion, next-generation sequencing for predictive ancestry and phenotype analysis is a great tool for use by forensics. Although it does have some limitations at present, the improvement of reference populations and further research into the effect of admixture on these populations will refine predictive results.